Hi, welcome to your lesson on logarithms. Here we have a big stack of logs, kind of in the mist, in the distance, a little bit hazy. Maybe that's what your understanding of logarithms is like, a little misty, maybe a little lost in there. But let's get your knowledge back up. Let's look at these again. Let's regroup and look at logs. So logs are a big idea in mathematics. For sure they are. They are a necessity for working with very large numbers, and they are a necessity for solving variables when the variables are in the exponents. So let's take a look. To begin, we're going to do a quick introduction. Logarithms can be used to help us deal with the manipulation of large numbers. So I just mentioned that, and hopefully we'll see some examples of that coming very soon. The word logarithm was coined by Scottish mathematician John Napier in the 16th century from the Greek word logos, which has many meanings, one of which is ratio. Logarithms are used by mathematicians and scientists in many fields, including finance and astronomy. And there is John Napier. A little bit of a look internationally. Logarithms do not have units, but many measurements use a log scale, such as earthquakes, the pH scale, human hearing. So there's scales for all these things, and those scales are based on what's called a logarithmic scale. Again, I hope we'll come to that stuff very soon, so you'll see how it works. All right, let's take some notes. So, investigation to begin. We are going to fill in these values in this table, and then we're going to fill in these log values. Well, let's begin here. 10 to the 0 power is 1. Anything raised to the 0 power is 1. 10 to the first power, 10. All right, 10 to the second power means 10 squared. 10 times 10, 100. I think you see a pattern emerging here very clearly. So fill it in, and then let me see if you know what 10 to the 6th power is. Okay, continuing on with that pattern, 10 to the 6th ends up being 1 million. 10 times itself 6 times. Okay, now let's jump to this side. And if you're familiar with logs, you might already know what these values are. But let's pretend for a moment we haven't seen logs, and let's grab our calculator. And on the calculator, you will find a log button. Let's find that button. My calculator ready to go. Here's the log button right here. That log button, you notice, does not have a base. But over here, we have log, and then this is base 10. So a quick hint for you guys. Since 10 is a very common base for logs, it is sometimes left out of the expression. Hence, when you see it written just as log of x, this is understood to mean log base 10 of x. So again, on our calculator, if we want to do log base 10 of 1, we'll just press log 1, and that means log base 10, okay? Any other base we'll have to enter ourselves, but this means log base 10, and that's what that button produces. Let's press enter. All right, we get a result of 0. So that first result is 0. Now try on your calculator, log base 10 of 10. Okay, that should produce 1. Next one, try log base 10 of 100. That should produce 2. Okay, I think we see a pattern going on here as well. So let's keep going up these here. Tell me what log base 10 of 100,000 would be. Well, continuing on with that pattern, the one I just asked about is a 5, and here we have 6. Now, there should be a clear relationship between these ones and these ones established here. So my question to you is, based on what you see here, generalize the relationship. If a to the power b equals c, so think of it like this statement here, then log base something of something equals something. So see if you can fill in this log statement here. All right, hopefully you came up with this. Log base a of c equals b. Let's take a look here. We have 10 to the 0 power equals 1. And then we can write log base 10 to the first power equals 0. And let's look at this third one as well. 10 to the second power equals 100. And here we have log base 10 of 100 equals 2. So notice that the base of the exponent becomes the base of the log, and the exponent is what we have on the other side of the equal sign. So we go log base 10 of this number equals the exponent. So that is what's called the definition of logs, and it's the first rule that we're going to learn and apply. So let's take a look. We have now talked about the definition of logarithms. And here it is. So the definition of a logarithm tells us when we have b to the power x equal to y, we can rewrite that as in the log statement, x equals log base b of y. So again, the base of the exponent becomes the base of the log. This thing on that side of the equation becomes that with the log, so log base b of that number of y equals the exponent. So always equals the exponent, okay? Remember that. In this case, b is the base of the exponential function, and here b is the base of the logarithmic function. So the base remains the base. Okay, and let's look at this in another way, because this helps some students remember how it works. When you look at a log statement, you can basically read it like this. The exponent that 5 must be raised to get 125 is 3. So in other words, you're looking at this part, cover up the 3 for a moment, ignore that 3, and you're saying, okay, I have log base 5 of 125. Basically what this is saying is 5 to what exponent will produce this number? And that's the answer for the log statement. An exponent of 3 will work. So again, there it is. And we know 5 to the third power is 125. So again, looking at this, 5 to what power produces this? Oh, 5 to the third power. So the answer here is 3. And those are interchangeable. You can go from log form to exponential form and back again, back and forth. All right, so that you know a couple more things about how to read this. When we write log base 2 of 8 equals 3, the number 2 is the base. Yes, we just talked about that. And number 8 is called the argument. And we can say the logarithm of 8 to base 2 is 3. Or simply, log base 2 of 8 equals 3. All right. The word logarithm is often abbreviated just log, right? So log base 2. Okay, so here's some for you to try. We have exponential form. What's the log form here? Well, that one is a log base 2, again, that base, of 32 equals the exponent, equals 5. How about this one? Go back the other way, from log form to exponential form. We have 3 to the 4th power, this is the exponent, 3 to the 4th power equals 81. Try this one. Log base 9 of 9 equals 1. And this one, 8 to the 0 power equals 1. How about this one? Log base 1/6 of 36 equals the exponent, which is -2. All right, and the last one we have here. Okay, and there's a whole other side here. I would say try some of these, and I'm going to ask you to tell me what the last two are. Okay, check your work along those, and double check. This is important practice to make sure you're proficient here. So there's the one I was asking for, and then that last one there, like that. Okay, with those, now you should be pretty quick switching from log form to exponential form, and from exponential form to log form. So now let's look at these applied in equations or expressions where we have a variable. So here's a log form given of something here, and we need to find out x. So right away we can change this exponential form. 3 to the 2nd power, because it's the exponent, equals x. Well, that obviously is 9. So looking at that one in exponential form gets us to the answer real quick. And here also, if you looked in log form, hopefully at this point you're doing this in your head. You're like 3 to the 2nd power equals, okay, well 9 is the answer. Okay, next one. We have x to the -4 power equals 16. So this one you might already be thinking of what that x might be, but we can also take it a step further. We know when we have an exponent like that, we can get rid of the exponent by applying a reciprocal exponent. So I see a -4, I'm going to apply a -1/4, because the law of exponents tells us we'll multiply those, and if you multiply those you end up with 4/4, which is just 1, and that would just be x. But if we apply that exponent here, we have to apply it here also. And that to the negative exponent will bring that to the denominator, and that 1/4 down there on 16 really means the 4th root of 16, and that means we have 1/2. Okay, so that one's a little trickier, and there's a lot of steps shown there, but once you become proficient with this, you probably won't have to take all these steps. You can even get to the point where you look at it from the beginning and you can get the 1/2. So think about that, but there's the steps laid out for you. Last one. It's just an expression, not an equation. So in that case, if we want to know what this equals, we're going to say, well, it equals something, which we don't know yet, but we're going to call it x. And then you can write an exponential form, And then 5 to some power is 625. You may know that power, but you can also rewrite this as a power of 5. And now you know the exponent must be 4. So hope that gives you kind of a window into how we use logs here, solving for these variables. With that, there's a bunch more for you to try. So again, I think practice is important here. Don't neglect this practice you can do. Pause the video and try some of these. And I'm going to ask you for the answer to this one first, and then maybe, let's say, this one. All right, so this one and this one. And from this side, this one. So let's say this one, and this one. Okay. All right. So here's a few more problems just to wrap this up. So this one says solve using calculator. So we have this exponential expression, 10 to some power is 500. Well, we know like 10 times 10 is 100, times 10 again is 1,000. So it's not going to be 10 to the third power because that'll be 1,000. And it's not 10 to the second power because that's 100. So it's something, the power here is something in between 2 and 3. So some decimal exponent. We can change that to log form. So log base 10 of 500 equals the exponent, right? So now we know that if we punch this in our calculator, we should get the exponent we need. So punching that in our calculator, again, we use the log button, and we don't need to use anything but this log button because that log button, again, is assumed it's log base 10, and I'm going to put 500 here. Close that parenthesis, press enter, and we get this decimal. And that makes sense, again, because 10 to the third would be 1,000, 10 to the second power would be 100, so we need an exponent somewhere between 2 and 3, and that makes sense right there. All right, great. So the answer, 2.7, if we round it. Now, the rest of these problems are going to be solving without a calculator. Let's try. Okay, changing that to exponential form, 7 to the x equals that. We have all these 7s here, so we have this common base. Let's try the rules we know about exponents here. So 7 to the x equals, this is 7 to the first, this is 7 to the half power. Now this, by rules of exponents, we can combine those, adding those exponents, right? So 7 to the x equals 7 to the 3 halves when you add those. And now we know x must be 3 halves. All right, using some of those rules of exponents, always good to know those rules and how they work. Let's try another one. How about this one? Okay, so change it to exponential form, 4 to the x equals this value. Now you're thinking, well, 4 to the x, that means maybe this is 4 to some power, because we're not allowed to use calculator. Okay, so 4, what power of 4 would that be? Well, if you investigate a little bit, you'll see it's 4 to the 5th power. And then now that tells you right away that the exponent must be 5. X is 5. Next one, we have this. Oh, a little trickier. I'll give you a hint. Change this to a fraction. Okay, so first of all, I'm going to put the 10 there. Again, when we see no base, we say it's base 10. Then 10 to the x equals this decimal. This, now changed to a fraction, is 10 to the negative 5th. I said change it to a fraction, but I never actually did it. This is actually 1 over 10,000, right? 1 over 10,000. And 1 over 10,000 is this, because it would be 1 over 10,000. 10,000 is 10 to the 5th. Bring that up, and we have this. So it's using laws of exponents. It's important you know these things, and that's that. Maybe I should have put that extra work there. Maybe I'll work at it now so you can see it. Okay, looks like I was prepared for that. I do have it on the side here. So here it is. 10 to the x, if I go from here to an alternative way, is equal to 1 over... Oh, I said 10,000, didn't I? Sorry, 1 over 100,000. Sorry about that. 1, 2, 3, 4, 5. Yeah, 5 zeros. There we go. And then 1 over 100,000 is actually 1 over 10 to the 5th. And then that can be brought up and becomes the 10 to the negative 5th. And then we get our answer. So that's a little trickier, but you can do it. Last one, I think. Try this one. What's x here? In this case, 4 to the x, again, changing to exponential form. 4 to the x equals this. Now you're thinking, well, it says no calculator, so this should be able to be rewritten as 4 to some power. So first we'll do 256 to the half power, because that's what the root turns into. And then 256 is actually 4 to the 4th. And now combining these, you multiply through. 4 times a half is 2, and that means x is 2. Great problems, great thinking here. Last one, try these 3. Let's give our answer. All right, so answer for A is here. Answer for B is here, and answer for C is here. So hope that went okay. There's another video, go to it now.